Understanding software virtualization. Software virtualization is a foundational technology in modern computing. It allows us to create virtual versions of computer resources, including hardware platforms, operating systems, storage devices, or network resources. Essentially, virtualization means creating a simulated or virtual computing environment instead of a physical one. This technology has fundamentally changed how we manage and utilize IT infrastructure. It provides a layer of abstraction between the physical hardware and the software that runs on it, making computing more efficient, flexible, and cost-effective. The core idea behind software virtualization is not entirely new, tracing back to the mainframes of the 1960s. These early systems used virtualization to allow multiple users to share expensive hardware resources. However, it was the advent of powerful x86 servers and sophisticated software in the late 1990s and early 2000s that brought virtualization into the mainstream. Today, it underpins cloud computing, data centers, and even desktop computing environments. The ability to run multiple operating systems and applications on a single physical machine is a game changer. For students entering the world of IT, grasping virtualization is crucial. Imagine running Windows on your Mac or Linux on your Windows PC without needing to reboot or partition your hard drive. This power to create isolated, independent virtual environments on a single piece of hardware opens up vast possibilities for testing, development, and deployment of software applications efficiently and safely. This video will explore the multifaceted role of software virtualization in modern computing. We will delve into what virtualization is, how it functions, and its significant benefits. By the end, you should have a clear understanding of why software virtualization has become such an indispensable component of the contemporary digital landscape. The mechanics how virtualization works. At the heart of software virtualization lies the hypervisor, a specialized software layer that creates and manages virtual machines, VMs. The hypervisor abstracts physical hardware resources and allocates them to VMs. There are two types, Type 1, bare metal, and Type 2, hosted. Type 1 runs directly on hardware, used in data centers and cloud environments. Type 2 runs on an existing operating system, like VMware Workstation and VirtualBox. Hypervisors isolate VMs, enhancing security and stability. If one VM crashes, others remain unaffected. Exploring types hardware virtualization. Hardware virtualization or platform virtualization involves creating virtual machines, VMs, that act like real computers with their own operating systems. The hypervisor software creates a virtual representation of the underlying physical hardware, including virtual CPU, memory, storage, and network interfaces. Each VM can run a complete operating system, known as a guest operating system, which can be different from the host operating system. This approach allows multiple operating systems to run concurrently on a single physical machine. For example, a single server could host one VM running Windows Server, another VM running a Linux distribution, and yet another VM running a different Linux version. Each of these VMs is completely isolated from the others, preventing software conflicts or security breaches in one VM from impacting the others. This capability is powerful for server consolidation, where multiple underutilized physical servers can be replaced by a single, more powerful server running several VMs. Hardware virtualization leads to improved server utilization, reduced hardware costs, and lower energy consumption. It also simplifies IT management tasks such as server provisioning, disaster recovery, and system maintenance. Hardware virtualization forms the bedrock of modern cloud computing infrastructure, enabling the dynamic allocation of resources that cloud services depend upon. Exploring types operating system and application virtualization. OS virtualization, or containerization, operates at the operating system level, allowing multiple isolated user space instances to run on a single OS kernel. These instances or containers have their own file system, processes, network ports, and resource limits, but share the host OS's kernel. Containers are lightweight and faster to start than traditional VMs, offering higher density and efficiency. Popular examples include Docker and Kubernetes. Containers are ideal for microservices architectures, providing an environment for deploying and scaling microservices. Application virtualization decouples applications from the underlying OS and hardware, allowing them to run in different environments. Methods include streaming the application to the user's device or running it on a central server with only the user interface transmitted to the client device. Benefits include simplified application deployment and management, enhanced portability, and extended lifespan for legacy applications. Application virtualization ensures continued access for users, improving operational continuity and reducing compatibility issues. Both OS and application virtualization offer significant advantages for modern IT environments. They enhance efficiency, flexibility, and scalability, making them essential tools for contemporary computing. Efficiency gains, better resource utilization. Software virtualization dramatically improves computing efficiency through better resource utilization. In traditional server environments, many servers operate at a fraction of their total capacity, leading to wasted hardware resources. Virtualization addresses this problem by allowing multiple VMs to run on a single physical server, consolidating workloads and driving up utilization rates. This leads to substantial cost savings, reduced hardware costs, and lower energy consumption. Virtualization also provides tools for dynamic resource management, reallocating resources between VMs based on changing demands. This ensures that applications receive the resources they need when they need them, leading to better performance and responsiveness. Improved resource utilization translates directly into reduced hardware costs and lower operational expenses. The environmental benefits are also noteworthy, as reduced energy consumption contributes to a greener IT operation. Virtualization maximizes efficiency far beyond what is typically achievable with purely physical infrastructure. It ensures optimal performance and resource utilization, making it a key technology for modern IT environments. Understanding these efficiency gains is crucial for leveraging the full potential of virtualization. Efficiency gains, isolation, and enhanced flexibility. Virtualization enhances computing efficiency through strong isolation and increased flexibility. Each virtual machine operates in its own isolated environment, crucial for security and stability. If a software fault occurs within one VM, the impact is contained within that specific VM, not affecting other VMs or the host system. This isolation facilitates running diverse workloads on the same hardware, useful for development and testing environments. Virtualization also brings unparalleled flexibility to IT operations, as VMs are essentially software files that can be easily moved, copied, and backed up. This portability allows for rapid provisioning of new servers, vital for businesses needing to respond quickly to changing demands. The ability to clone VMs simplifies tasks like creating test environments that mirror production setups. Virtualization extends flexibility to disaster recovery and business continuity, with VMs regularly backed up and replicated to a secondary data center. Features like live migration further enhance flexibility, allowing for planned hardware maintenance or load balancing without impacting service availability. This ensures that critical applications remain accessible to users at all times, improving overall system reliability. Understanding these benefits is essential for leveraging the full potential of virtualization. Powering growth, virtualization, and scalability. Scalability is a critical requirement for modern computing environments, and software virtualization plays a pivotal role in achieving it. Virtualization enables dynamic and granular scalability, allowing organizations to adapt their resources precisely to their current needs. It facilitates both vertical and horizontal scaling, ensuring applications maintain performance levels even as demand fluctuates. This enhanced scalability is a cornerstone of cloud computing, enabling on-demand resources for customers. Businesses using cloud services benefit from this elasticity, paying only for the resources they consume. This agility allows businesses to innovate faster, respond to market changes more effectively, and manage their IT costs more predictably. Understanding virtualization's role in scalability is crucial for leveraging its full potential. Virtualization in the real world, practical applications. Software virtualization transforms how businesses and individuals use computing resources. Major cloud providers like AWS, Microsoft Azure, and Google Cloud Platform use virtualization extensively, offering virtual machines on a pay-as-you-go basis. Data centers have been revolutionized by virtualization, leading to significant savings in hardware, power, cooling, and physical space. Desktop virtualization, or virtual desktop infrastructure, VDI, allows organizations to host desktop operating systems and applications on central servers. Users can access their personalized virtual desktops from various devices, centralizing desktop management and improving security. Virtualization is indispensable for software development and testing, allowing developers to create multiple isolated virtual environments on their workstations. Automated testing frameworks can leverage VMs to run tests in parallel, speeding up the quality assurance process. Snapshots allow developers to easily revert to a clean state if a test corrupts the environment. Understanding these practical applications is essential for leveraging the full potential of virtualization. Conclusion: the indispensable role of virtualization. Software virtualization has profoundly reshaped modern computing, unlocking unprecedented levels of efficiency, flexibility, and scalability. It empowers organizations to make better use of their IT resources, reduce costs, and respond more rapidly to the ever-changing demands of the digital world. Virtualization is the engine driving scalability in modern computing, enabling both vertical and horizontal scaling of applications and services. It facilitates agile development and testing environments, accelerating technological advancement. Understanding virtualization concepts and their practical applications is essential for anyone in the field of computing. Its influence will continue to grow, enabling future innovations and efficiencies in the years to come. If you learned something new, like the video, share your thoughts in comment section, and don't forget to subscribe the channel for more related videos.